Tony got his bachelor's degree in physics at Stanford University, and then his PhD in physics at UC Berkeley. He spent some time in Yorktown Heights as a member of the IBM research division. And shortly thereafter, he joined the faculty of Columbia University as a professor of physics and electrical engineering. I do have a really nice shared history with Tony, in that I took his statistical mechanics class in my undergraduate years and later became his PhD student and helped oversee his most recent transition to Stanford University in 2015, where he took on a dual appointment as both the professor of applied physics at Stanford and a position at the SLAC National Accelerator Laboratory as a professor in photon science. Tony's research in surfaces, interfaces, and 2D materials generally apply spectroscopic methods, a lot of laser spectroscopy, to further understand the very exciting world that is reduced dimensionality material systems. And his work has been recognized by such awards as the Isaacson and the Shallow Prizes of the APS, among many other distinctions. So with that, I will hand the floor to Tony, and thank you for joining us.
Okay, well, great to see all of you. A lot of familiar faces, and thank you all for coming to let me share with you some of the things we've been doing in optical spectroscopy of 2D materials. So it's really nice to see this confluence of a national lab and university. I'm also in that sort of configuration with Stanford and SLAC, and something that I think is really, beneficial on both sides. Well, I would like to tell you a little bit about some of the things we've learned with in trying to understand two-dimensional semiconductors. And I will be focusing as an optics guy on excited state properties. I'll tell you something about what we're now understanding about the properties of monolayers, and also a little bit about the particularly exciting new phenomena that emerged just by stacking these materials together. I'm not going to be talking about the maybe best understood and most studied system, which is graphene, and kind of ushered in the concept of monolayer 2D materials, but I'll talk about what's probably in second place and attracting a lot of interest for, I think, pretty good reasons, which is a model system which is two-dimensional but has semiconducting properties. And there are things in this category of moly sulfide and transition metal here with combined with sulfur, selenium, tellurium. And this is what we call a monolayer. It's a stoichiometric monolayer. It actually looks a lot more complicated than graphene, you might think. But if you take a top-down view of the structure, it has this kind of honeycomb lattice, just like graphene. The difference is that instead of having the same atoms on the A and B side, you have metal atoms on one side and the chalcogens on the other, but the chalcogens are displaced a little bit vertically. So actually, from the point of view of symmetry, it's very similar to graphene with the broken AB sublattice, and is actually identical in terms of two-dimensional symmetry with hexagonal boronitride. So it wasn't unnatural to try to look at these materials after people recognized that you could exfoliate graphite into graphene, because these were also materials that were understood to be layered. Some of you may know the moly disulfide is often used as a vacuum grease, so you can take it and increase the ability to move things in ultra high vacuum, and it's because you can shear the layers. And it turns out a little bit like graphene at a sort of a high level. You would say the properties in the monolayer are not drastically different from the bulk material. It's not like trying to get a monolayer of silicon, which would have very little to do with bulk silicon. But the differences are still very interesting and make the study of what happens in 2D very worthwhile. And to give you an example, this was how we got started in the field, and actually Albert Ragosi contributed to these studies. We exfoliated some of moly sulfide on a patterned substrate here, and you have very strong light matter interaction. So basically with the eye, you can see the presence of a monolayer here, and this is a little bit of a thicker flake. And like graphene, it has good mechanical properties. It goes right over these holes. So that was very reassuring and nice. But the part that was a bit surprising was when you looked at the emission spectra, instead of reflection, you illuminate with the laser and you look at the light that comes out. You saw a very strange effect, which is that you got quite a bit of light emission, bright emission from this thinnest part of the material, and you got basically no light emission from the thicker part. So this seems a little bit counterintuitive. You clearly have less absorption. Why do you get more light emission? Well,
How thick is it, or the thick?
oh, okay. So thin means one of those stoichiometric monolayers, which we consider to be about 0.5 nanometer in thickness. That would be this distance in stacking. So yeah, you could think of this as 0.6
And is
nanometers.
the other one 2 monolayers? Or
This was actually like 3 or 4 monolayers, but yeah, of course, the next thing we did was to study them systematically as a function of thickness. So you could actually think of innumerable reasons why you might get a lot of light emission from this, and then in monolayer it's damaged, it's whatnot. You get less than the proportional fraction. But why do you see much more? Well, it turns out there was only one good explanation for this, and that was the correct one. It was known that the bulk materials have an indirect gap, which means light emission is inefficient because a photon has to be involved to conserve momentum. Well, at the monolayer level, you actually transition to a direct gap material with efficient light emission. So from that point of view, it actually looks quite a bit like what happens in graphene, where these Dirac cones that you've probably all heard about reside at the corner of the Brillouin zone. So you have a kind of a similar configuration here, but you have a direct gap, and that's something distinctive to the monolayer. The other thing that's different is you don't have this linear dispersion. You have regular parabolic bands. And unlike carbon, where you have weak spin-orbit interactions, these are heavier elements, and you have significant spin-orbit interactions with a big splitting in the valence band and a small splitting in the conduction band. Another interesting aspect of this, which I'm really not going to cover today, is that you have two degenerate valleys related by time reversal symmetry. And it was predicted and demonstrated early on that you actually have a very interesting possibility of selectively exciting one of the valleys or the other valley using the helicity of light. This is called valley circular dichroism. And that's an interesting aspect of these materials I won't be stressing today. So that's sort of a thumbnail sketch, zeroth order of the expected band structure, 2D materials. Well, after you see the contrast, you see light emission, you want to go to the next step, and that's measuring the absorption spectrum. And here's what we got fairly number of years ago already. You actually see this very, very strong peak at an energy around the band gap, and you see another broader feature, similar feature at a bit higher energy. This splitting is actually related to the splitting in the valence band from spin orbit interactions that I just mentioned. So a very nice structured spectrum. But for those of you who might have taken a course in solid state physics and optical properties, there's sort of a paradigmatic way that you describe to first order what the optical spectrum should look like, and that is you count states. So you look at the joint density of states, and famously, if you have a parabolic band in 2 dimensions, you might know that you get a step function for the joint density of states. So in the simplest picture, this red line is what the optical absorption spectrum should look like. You have to get to the band edge, and then you have a constant absorption. And a lot of the 2D materials like quantum wells that are, we would say, more quasi-2D, thicker, but the electrons are confined, actually look quite a bit like this. So you would have to say this is not very good agreement. What's missing from this? Well, this is a correct description of uncorrelated transitions for uncorrelated electrons, where the states basically look like block waves of the electrons in holes. But in fact, you expect to have interactions between the electron and the hole. That's an excitonic correction. Typically, that's fairly weak in bulk materials. Now, of course, with all of the NIST expertise in atomic systems, you could say, why will the electron interacting with positive charge be weak? The reason is you've got a lot of other electrons around. So there's this dielectric screening. And if you just scale the hydrogen binding energy, for example, you divide by the square of the dielectric function, which is a factor of 500 or so. That turns out to be a lot weaker in 2 dimensions. So we understood that this thing is clearly a signature of having a very strong excitonic interaction, much more pronounced than you typically see in semiconductors. The excitonic effects are well understood, but they're usually predominant at low temperatures. So we understood early on that was hallmark of strong excitonic interactions. But then the next question everybody would ask is, well, how high is the exciton binding energy? And the interesting thing is what you'd normally do is compare the position of this peak with the onset of the continuum absorptions. You'd get excitonic peaks and you'd get band-to-band transitions. But as you keep increasing the correlation effects, the excitonic effects, you kind of lose the band-to-band transitions. So you don't really know what to compare this with. But as it happened, if you look more closely, you see down in this region that there actually are some higher lying excitonic states. So just as in atomic spectra, you have the lowest transition, you have higher lying states. And those could be extrapolated to the ionization energy. So this told us that the exciton binding energy was several hundred millivolts. So obviously not as strong as binding of electrons in atoms, but much stronger than you normally see in bulk semiconductors. And in particular, it means that all these excitonic effects are dominant at room temperature, not only at low temperatures. If we look at this in a bit more detail, we plot up the energy of these different excitonic states. So these are actually all 1s states, and since you're creating the exciton, unlike a spectrum of hydrogen where the atom already exists, you see the 1s state, 2s state, and so forth. And if you try to plot them against the two-dimensional hydrogenic model, which I don't show here, you would have absolutely terrible agreement, because the first excited state for hydrogen is something like 85% of the way to the ionization in 2 dimensions. So you might ask, why does this look so different? And the answer is that you have to still take into account dielectric screening of a thin layer. So it's not a homogeneous reduction. And in a simple analytic approximation, that gives you the so-called Keldysh potential. That's the electron hole, the charge interaction in a thin sheet in 2 dimensions. And if you put in this somewhat complicated looking potential instead of a 1/r potential, then you can predict these excited states quite nicely. So that's a kind of effective Hamiltonian approach to the problem, but it describes what's going on quite well. And you can see here that the extrapolated binding energy is really quite significant here. The corresponding excitonic wave function is relatively localized compared to what is seen in other systems. As the binding energy goes up, you have something more localized, but it's not in this limit where you would think of a big distortion and localization of the electron in a particular site. So it's sort of on a scale of a couple nanometers, and I'll be coming back to that. One of the marvelous things about 2D materials is all the ways you can access them and tune them and modify them. One of the simplest things is to add more charges by a gating effect. So if you put an electrical contact on the 2D material and you change the potential with respect to the substrate, you change the charge density. And one then immediately saw signatures of these 3-body excitonic states. So this would be like the hydrogen anion, which also had a actually fairly significant binding, and also 4-body biexcitonic states. And this is the corresponding wave function representation of the wave function. Of course, the biexciton is sort of like the hydrogen molecule, but it's a little bit different in the sense that you can't use a Born-Oppenheimer approximation, right? So all 4 of the charges are light. And consequently, when you plot this thing, you have to sort of make projections into lower dimensional space. And these spikes would represent likely positions of the hole, and then this would be the electronic charge distribution. And this is actually looks very much like a ground molecular orbital, right? You get enhanced charge density in this region, and that kind of holds the two positive charges together. It's also interesting in the context of quantum information science, because this would be a building block for a solid state source that produces correlated pairs of photons. So since you have two quanta of energy in this, in a 2-photon decay, you're going to have correlation effects. And this is something that people are now exploring. So the spectroscopy of these things has actually improved quite a bit by getting better samples, and we now know better how to protect them by encapsulating them in other van der Waals materials like this insulating boron nitride. So this is then an emission spectrum where the vertical axis is changing the charge density by gating, and the color scheme shows the different emission features. So we can actually see quite a few different things: a neutral exciton, these charged excitons that I mentioned, bi-exciton, charged bi-exciton. And also what's interesting is that line width of the features is continuously decreasing, but it's actually getting to the fundamental radiative width. So there's some spin forbidden dark states here, and this width corresponds to various non-idealities of interaction with phonons and inhomogeneities, but this width is actually clearly less than the width of the other features. So we're mostly seeing radiatively broadened transitions in the nicer samples. So we've begun to understand the different types of species that you can produce under different conditions of different charging and different excitation conditions. This regime where you have just a radiatively broadened line is actually quite interesting and unintuitive at first. It's one of these things that happens, I think, a lot in physics, where at first it sounds very peculiar, and then about a week later you say, of course it's that way. But maybe it took me a month. But one of the questions is, if you have this radiatively broadened line in 2 dimensions, then what happens if you send light resonant with the radiatively broadened line? So probably, or at least for people looking at optical properties of solids, you always start by saying, well, there's some penetration depth, and that penetration depth is typically on the order of a wavelength. So a thin layer of nanometer, yeah, you'll perturb things, but not too much, a few percent. And famously, graphene has an absorption of 2.7%. But that's very far from a radiatively broadened line. So what would happen if you're resonant with the radiatively broadened line? Anyone like to hazard a guess here?
It would be cheap because yes.
Pardon me?
It would get reflected.
Yes. So it's sort of like there's no damping. So it's basically an infinite response. And that was recently shown in a nice paper by Hung Park and collaborators, and they didn't get 100% reflectivity, but it was actually getting pretty close to 100% reflectivity. And basically, radiatively broadened means there's no other damping in the system, so it's like an infinite conductivity. And you under those circumstances, you get 100% reflectivity. So a little unintuitive for people used to shining lasers at solids. Totally intuitive if you start thinking about reflecting a radio wave from a sheet of metal, right? That's an analogous thing, because obviously the sheet of metal is a lot less than the wavelength in size, but you can get unity reflectivity. Also, it means you have a strongly negative dielectric function near the resonance, so you can have different types of bound excitations. So this is something people are just beginning to explore. I should say that to get to this radiative limit, you do have to be at reduced temperature. So you need a good sample, but at room temperature, you have a lot of phonon scatterings. You're not in this limit. But it's not extremely low temperatures. It's sort of 10 Kelvin kind of range. So it's quite an interesting regime to explore, I think. Well, I'd like to tell you a little bit about a recent chapter where we applied a different experimental technique, one not so widely used. And that aims to actually understand optical excitations in a more comprehensive way. So everything I described before up to this point involved absorbing or emitting a photon, right? That happens predominantly if you can conserve momentum. And the momentum of a photon is a lot less than the momentum of an electron in the crystal normally. So what that means is you see we described these then as vertical transitions. I mean, there's a slight momentum from the photon, but essentially vertical. And these other things are the indirect transitions that I alluded to that are quite weak. So you don't really have very good or direct signatures of all of the excitations that might involve electrons in one valley and holes in another valley. It turns out there are also these spin splittings, so you have spin forbidden transitions that are also very weak or unobservable that you might not be able to see. And there's actually even another factor, which is for the optically allowed direct transitions. That is only if you're right at the bottom of a valley. So if you have an electron with a bit more kinetic energy, then its kinetic energy is too high, or you'd say the exciton is moving along too fast and it can't disappear and transfer that momentum to a photon. So there are actually a lot of different types of dark excitations in these systems. So the thing you can see in a kind of direct way are bright excitons with the small amount of momentum, and all these other things are harder to see. Well, the most widely used technique for exploring band structure and electrons, in different parts of the Brillouin zone in condensed matter physics, I would say, is photoemission spectroscopy. You eject the electron and then you resolve the energy and momentum. And the question is, can we use this not to image the ground state of the material with the electrons completely relaxed, but to somehow image the excited states and the excitons? So this requires a little bit of a modification in the sense that you need to have an excited material. To have a reasonable level of excitation, you have to give it a good jolt of excitation, and you're not going to preserve a high level of excitation in steady state. So you want to do that with a pulse, and then you're going to want to use not angle-resolved photoemission spectroscopy, but time-resolved angular photoemission spectroscopy. So this is an interesting technique that has gone through various evolutions and I would say has been quite challenging experimentally, but with some of the advances, both in the electron analysis and collection and on the laser side, it's becoming a pretty well-developed technique. And in the context of what we're doing, it can give you a comprehensive picture of not only the optically bright, but also all the other dark excitons, their valley character, dynamics. And interestingly, I would assert a very direct imaging of the excitonic wave function. You'll see what I mean in a minute. Well, just to remind you, the usual photoemission, angular resolved photoemission setup, you have some incoming photon that has an energy appreciably above the work function. It ejects an electron, then you detect the energy and angle of the electron, so you get the full momentum of the electron. Then you work your way backwards and you can figure out the energy and momentum that the electron had while it was still in the solid. And in the case of 2 dimensions, it's really very nice and straightforward. You don't have to worry about any projections. It directly translates the momentum in the plane into the momentum in space, and you also know the energy of the electron. Now, this requires a significant amount of modification, as I said, to do the experiment in this time-resolved fashion. So you have to replace the usual CW source, typically from a synchrotron these days, with a pulsed laser. To do this in a nice way, the photon energy can't be too low. You have to be well above the work function. So something like a 20 eV photon is very nice, and producing short pulses of 20 eV photons and with high repetition rate to get good signal to noise is kind of a long story that some of you might know about. I won't go into it, but using amplified laser systems and high harmonic generation, there's a way to do this. And then there are also advances in the way you do the collection here. So I should say that all of the credit for the nice instrumentation doesn't go to us. We were the guys who supplied the samples, but we had a wonderful collaboration with Keshav Dani's group at Okinawa Institute of Standards and Technology in Japan. And you can see some of the parameters, but just to skip to the results, this is the kind of band structure mapping that you can do of a two-dimensional material. This is the unexcited system. Actually, you get brightest emission at the zone center, which is not the highest part of the valence band structure. So a little bit weaker signals here. Then there are all of these conduction bands up here, but they're all dotted lines. So there are no electrons in them and you see no signals. This is all modeling. The question then is what happens if we photoexcite the system? So this is just putting the sample in the chamber without any photoexcitation. Suppose we photoexcite it, we create optical excitations. What happens then?
So
Yes,
why
Bill.
is this symmetric?
Oh, there are actually some reasons. So there's a slightly different selection rules. I mean, the band structure is selective. The intensities actually do have some inherent asymmetry because you don't have full mirror symmetry in the problem. But mostly it's signal to noise, actually, Bill. So you'll see actually this was I guess the data were like 3 years ago, and actually they get more and more symmetric and look nice as we go on. It was sort of I have to say, a sort of heroic experiment being able to see anything. But this is the exciting thing. We actually see electrons that are sort of in the range of the predicted conduction bands. And this was taken at some delay time after we photoexcited the system. So we expected to have electrons here, which is the direct band gap. We actually weren't so sure that we'd have electrons over here in a different valley in the Brimwell zone. Certainly, we didn't excite them there. We had the vertical excitation. So this is clearly a signature of excited electrons. Just to give you an example, this immediately told us there was another type of exciton here, which had an electron in this ancillary valley here, called the Q valley. And we could immediately use that to study the dynamics. So when we looked at photoemission at an early time, we actually we promptly saw the signal from the valley momentum space where we excited the electrons, the K valley, but only after a delay time of a couple hundred femtoseconds did we see this new kind of exciton form. So that was an inter-valley scattering process. And in fact, we'd had various clues that might exist in terms of broadening of experimental lines and temperature dependence of broadening and things of that sort. But this gives you a very direct picture of the character of the excited states in the system.
So, yeah.
Yes, sure, please.
So I'm writing, the phonon is involved in this.
Yes,
this
that's
process,
right. Yeah.
So is there do you have any idea of what sort of mode this phonon represents? About the structure?
Well, I mean, what you
a question that can be asked, is there
yeah, I mean, it's the one thing you know very directly is the momentum of the phonon, right? Because it scatters the electron. And then, there are actually a limited collection of possible phonons. There are acoustical phonons and optical phonons, and their calculations of the relative coupling strength of these. So you actually know that you're dominated by optical phonon scattering. And if you look then at the dynamics here, it can tell you about the electron phonon coupling strength. So the interesting thing is we did a study previously of the variation of the line width with temperature for exactly this exciton. And we saw the onset of a broadening that you could correlate with an activation energy of a phonon, but it was all a pretty indirect story about what was going on. We could really only understand the results if we assumed there was another valley and you opened up another scattering channel. So this was like a missing piece of the puzzle that then allows us to have confidence that what we're seeing in that broadening is the influence of a phonon that connects the K and Q valleys. Well, let me talk about maybe an even more basic aspect of this. If we just focus on the K-Valley signal and we resolve it in momentum space, we find you get some distribution here. It turns out to be 0.07 inverse angstroms in width. And the actual instrumental resolution of the setup was 0.001 inverse angstroms in width. So why do you get a finite width of the distribution of the electrons? Well, one of the things you think of immediately is, you're doing this experiment of finite temperature. The excitons will have some kinetic energy. They're going to be moving around. But when you calculate how much momentum broadening that would give rise to, it's absolutely negligible compared to what we see. So you kind of double check, is this really correct? This is the experimental resolution. It's really far below what we're seeing. The answer is yes. So does anybody know why you might see a finite width in momentum space if you're emitting from these cold excitons that are not moving very significantly? No, it's actually a characteristic just of an individual exciton. So I should sort of go back. One of the things that people wonder about is, should you even see a photoemission signal from an exciton? I thought it was a neutral quasi-particle. Well, it's sort of like, can you see photoemission from an atom? And the answer is yes. It's sort of neutral overall, but it has an electron in it. And what's happening here is you can think of this localized electron as a superposition of many block waves, right? That's how you get the correlation between the electron and hole. So if you really just had, an electron at the K-Valley and not an exciton, then you would have a sharp signal sitting at the bottom of the band. But the exciton is actually this localized wave function that correlates the electron and hole position. So you definitely expect a width corresponding to the intrinsic decomposition of the exciton into different momentum states. And this is a corresponding theoretical estimate, which, yes.
One question.
Sure.
So for the exciton, you have the bore radius.
Yes.
It's broader than K. That's true.
Yeah, that's.
But then you're doing ARPES with 22 EV.
Sure.
So we are far away from our hydrogenic lines.
Well, you're going into. I mean, the assumption in ARPES is you're going into an external plane wave state. I mean, of course, there are various details about.
Yeah. So I was wondering how this 22 EV, and I'm talking about an exciton that has like about 2 EV.
Sure.
So.
Well, you can think of. I mean, the way we think of it is that you have. For the moment, let's assume the hole has very high mass, so it's not playing a big role in this. So then you have these different block states, and you're basically projecting them out into plane wave states in the vacuum. I mean,
then I don't need to think about excitons because excitons will be at a very, very low energy. So these are the excited states of my dielectric.
Well,
maybe I'm missing.
No. I mean, let's maybe step back and say, suppose you have an electron at 2 EV in the conduction band. What would happen then? Then if we're sitting at the very bottom of the valley, it would have a defined amount of momentum, and you'd see emission in the narrowly directed electrons going in narrowly directed way. The 20 EV that you add to it gets them out, it gives them the energy of the work function and gives them extra kinetic energy. But you sort of subtract all of that out, so you figure out what the initial state was. So, you measure the final state, you assume your conservation of energy and momentum, you work backwards. So you do more or less the same thing. It's just the exciton is a superposition of many of these block states. That's sort of the idea. Or you can say, it's kind of a Fourier transform looking at the different momentum components. But of course, you have to subtract out the characteristics of the photon. At normal incidence, a photon has no in-plane momentum, but you do get the 22 EV added energy. The bandwidth in energy is not really that narrow, but it doesn't actually affect the momentum distribution. You're worried about that. Maybe we can come back to it.
And what is work?
Yeah. The work function's about 5 EV, 4 or 5 EV. That's one of the challenges. It's very easy to do these laser experiments with like a 6 EV photon, but you barely get out the solid. So actually, when the electron has a lot of in-plane momentum, which has to be conserved, you need even more energy than the work function. If you go through the math, you need about 10 eV or something. So yeah, then if you take the Fourier transform, this tells you about the size of the electron. The size of the electron is the size of the electron-hole correlation. That's what it means more technically. And this was quite similar to those model Hamiltonian calculations I showed you earlier. Okay, so as I highlighted, one of the nice things about 2D materials and also optical properties is you have huge number of interesting ways you can understand the physics more deeply by external stimuli, and also manipulate the system and have a pathway to make it do something useful. This is just a little enumeration. I mentioned briefly carrier doping. You get these positive, negatively charged trion species, magnetic fields, way of modifying spin forbidden transitions. Strong electromagnetic fields are actually also a very interesting topic in this area. I'll just briefly mention two that I think are kind of distinctive and maybe kind of a simple story. One is the role of external media, and the other is how you can use strain to good effect. Okay, so let me first say a word about the external media. This is the highly simplified picture of the excitonic states, the ground 1s state and the 2s state. And the notion is this is sort of roughly the scale, that the exciton is sort of a nanometer or so, as we were just discussing, 1.5 nanometers. The thickness of this medium is something like 0.5 nanometer. So in the ground state, you can already understand that there's fundamentally no way to decouple the excitations from the external environment. So van der Waals materials are not chemically reactive. In the ideal case, they have no chemical reactivity, but you can't just decouple electrostatics from the external environment. So you can understand that there's always going to be some sensitivity to what's outside of the material, even if you don't have chemical reactivity. And if you go to the excited state here, where the electron-hole separation is a lot more, then you would anticipate that this effect will be even stronger. You just can't decouple it from the external environment. And it's not typically the way we think about bulk solids, other than through very classical couplings like temperature and pressure and things of that sort. We don't think that the material properties are really influenced by what they're sitting next to. But here you can understand that is not going to be completely true. Let me show you just experimentally a very straightforward kind of experiment. We have a monolayer of one of these semiconductors, and then we put a little bit of graphene on top of it. And the scale is big enough that we can shine our laser in different spots and do the spectroscopy and just compare what happens. So this is an illustration of the lowest lying state, this 1s state. And here's the feature you get with the material without any graphene on top of it. You put the graphene on top of it, it shifts down to lower energy because you get sort of a lower energy scale from the reduced Coulomb interactions. Not such a big shift because a lot of the screening is inside the material, but it's very clearly present. On the other hand, if you look at the excited state, which is this feature, it actually shifts by quite a lot, by about 100 millielectron volts. Pretty big scale in the energy change just by putting this external material. And it's not that you're changing the chemical bonding or anything of that sort. You're just, we would say in the language of condensed matter physics, we'd say you're modifying the many-body Coulomb interactions in the material, and that's causing changes in the excitonic spectrum and band renormalization. So this is actually kind of an interesting situation. If you plot then the extrapolated band gap, where you have this semiconductor monolayer and you go under a piece of graphene, then the quasi-particle band gap goes from about 2.35 eV down to 2 eV. So just by putting something on top of it, we've kind of created a lateral confinement of the electrons. Now, this is actually something that's not that easy to do otherwise. Of course, there are electrostatic methods that you might use, and there are classical things like doping, but that's pretty hard to control. So this, to my way of thinking, is a kind of distinctive feature that emerges just because the dimensions are so small that you really can't decouple the local electrostatics. And this is kind of an alternative to things that you see like this in the literature, where people try to grow one material into another. And of course, that's very interesting, but it also tends to be extremely complicated right here at the boundary, and things rarely work out the way they do in PowerPoint in reality. On the other hand, Feng Wang at Berkeley, for example, recently showed that you could make actually a dielectrically controlled heterostructure where you saw PN sort of asymmetry just by putting a different dielectric material in one half of the semiconductor compared to the other. The other thing to be said is actually, even if you don't think this is such a nice thing to do, it's going to happen whether you like it or not. So if you're designing structures that have different materials, this will be one factor where even without chemical modification, the local electrostatics will slightly change the properties, inherent properties of the 2D material. Okay, and a local variation of strain. So first of all, in 2D material, strain is a favorite tuning parameter because it's pretty easy to apply and it does a lot. So this is just where we apply up to 2% strain, and we look at the optical emission spectrum. As you strain it and the atoms are further apart, it shrinks the band gap a little bit. Famously, if you do things right, you can get really high strains in 2D materials, and change things even whether from a semiconductor to metal, things of that sort. But what's also very distinctive about strain in 2 dimensions is you can control it in a very localized way. That's a lot harder to do in 3 dimensions. So that means that you can have a route to do very local modification of the material and the band structure. And this is a kind of thing a lot of people have been doing. They've milled some kind of pattern in the substrate. This is obviously very exaggerated here, but you have some kind of protrusion, and then you deposit your monolayer on top of it. And that's going to create an inhomogeneous strain field. And in particular, you're going to see a lot of strain up here, which will lower the band gap. This, we discovered, tend to be a pretty perturbative thing, and you do get a lot of changes, but some of them are related to tearing the material typically. We developed this sort of upside down version of this thing where we dug a little bit of a hole in the substrate, and then you could easily put the material on top of it without tearing it. If you subsequently pressurize it, you can actually make it go down into this hole. I mean, this is also, I should stress, a very exaggerated vertical scale. And you create this corresponding potential well. So there are lots of interesting ideas about how you can locally pattern things and transfer the strain pattern. So why would you want to do this? Well, this is an illustration where we made holes in different spots, and we pressurized the materials. And then we see the optical emission is localized at these holes. Well, actually, it's not totally localized at the holes, but we filter the emission. We look at the longer wavelength component, and then we see the emission that's coming from the region of reduced band gap. It's also the case that actually the excitons move around and they fall into these traps. So both of those things are going on. If we look at the corresponding emission spectra, this is from the region of the sample away from the holes, and this is in the holes. So we've shifted the emission by a significant amount. Otherwise, in this case, it looks fairly similar. It's a sort of a shifted version of this. This turns out to be one of those try-on features that I talked about before. So we can pattern the behavior, but you would say in this regime, there's nothing strikingly different about it, just localized. But what's interesting is if we go, I'm still getting used to this thing. If we go to a much smaller lateral dimension and we look at the emission spectrum, it starts looking really different. So this is 250 nanometers. This is more like a 20 nanometer hole. And then we see these very sharply defined features. So there actually are several reasons the line gets sharper. Some of them are sort of experimental in character, that you always have some inhomogeneous broadening. If you make the emission area very small and you look at only one of them, you basically eliminate inhomogeneous broadening. But there's also a more fundamental reason, which is actually the radiative rate when you localize excitons strongly drops. They become less efficient in coupling to these outgoing plane waves. So this width that we see now is far below the radiative width you see for the delocalized excitons. And in fact, this is the regime that we call quantum emission. So in addition to the fact that you get this confinement-induced line narrowing, the trap is small enough that there's basically only room for one exciton. So you can't have two excitons in there simultaneously, and consequently, you can't emit two photons until the exciton is regenerated. And there's a standard way of showing that kind of thing, which is a photon anti-bunching experiment. So you look at the probability of measuring two photons at the same time compared to measuring a second photon at a delayed time. And you know, in the ideal case, this would be zero, but clearly there's a strong anti-bunching effect. So this thing is actually what we call a single photon emitter. You can reliably excite it and be absolutely sure you only get one photon. It's basically like an atom, it's the same, but the difference is that this is a quite convenient experimental platform which could be driven not only by light, but also by electrical excitation. And consequently, that sort of capability is quite interesting. And you can also then working towards the possibility of having whole arrays of these quantum emitters and looking at their coupling. So this is really facilitated by the localization of strain and the control of the placement of the excitons and accessing this very small lateral scale.
So,
yes.
I mean, you said 20 nanometers for these
yeah.
structures. Is there like a minimum kind of size for these wells that you can, based on the flexibility of your material?
Yeah.
Maybe one of the direct is that what's the 0-point fluctuation of these traps?
Right. So
spacing.
Yeah, it's actually sort of it's a non-trivial question to answer of sort of how small the trap has to be so you get quantum emission behavior. So certainly one criterion, the one that's easy to calculate, is like the level spacing of the lateral motion of the excitons in the trap. And you want that level spacing to be high enough that your experimental temperature, you can be in the ground state. So that's an easy thing to think about, and you can estimate it. The thing that's a little more subtle is what prevents you from having two excitons in the trap. And that's like an exciton exchange interaction. And a little, yeah, but so if you want quantum emission, you really need to satisfy both of those criteria. So that seems to occur for a trap size on the order of 10 or 20 nanometers at a reasonable temperature. From the experimental point of view, the part that's a little bit tricky is not making a very small dip. So actually what's very nice about this is that you're kind of you don't have to have a perfect topography to get a trap. Of course, it'll change the profile of the trap a little bit, but it's not like trying to chemically modify the sample where if the one dopant is not quite in the right place, it's going to make a huge difference. But what isn't so easy is if you just try to make the same depth of the well, there's a very easy scaling relation. You more or less keep the same aspect ratio. It turns out, however, that it gets harder and harder to pressurize it and make the film bend. So that actually, the pressure need scales like the inverse of the diameter. So it's extremely easy to pressurize like a 250 nanometer. It gets harder and harder as you go down. So our original idea, which was, very pleasing, I think, was literally pressurized by putting an inert gas in there, and just like a balloon, we push it in there. It works great if you're like at 100 nanometer scale. You more or less have to use different techniques when you get to very small scale. So that's kind of the threshold of understanding what we can do experimentally. Okay, so let me use the last couple of minutes here just to say something about what's been really inspiring a lot of people in the community, and that's the possibility of combining these building blocks. So we're getting to understand quite a bit about the characteristics and excited states of the individual layers, but all sorts of new possibilities emerge when you stack them together. And I think Albert mentioned early in my career, I did a lot of work in surface science. So I was sort of dubious about people who produce beautiful pictures like this in PowerPoint. And I said, well, reality is not going to be so kind. There's going to be a lot of pump oil in between these layers and other things, that's not going to work. And I have to say I was sort of partially correct, but functionally largely incorrect. And it was an extremely unusual phenomenon in physics. It was like better than expected. I mean, almost everything is worse than expected. There are 100 problems and you only thought of 50 of them. So why is that? It's because there was some pump oil, but the pump oil was extremely mobile. And basically when you stack the things together, you get regions that actually look like this, where the materials are actually in ideal contact. Now, there's a part that doesn't appear in the picture in the paper, which is like a bubble of contamination, but you can still do nice experiments. So you have a huge number of possibilities. You can combine all sorts of different material systems with insulators, semiconductors, semi-metals. And it's not like chemistry, you don't give them a choice. You just put them there and they can't argue with you too much. And you can stack them more or less in the order you want. And of course, you also have this degree of freedom of the twist angle. So, you can align the Brillouin zones relative to one another and get different moiré patterns as a result of that. So just to show you in the context of optics how some interesting new things emerge, we took two of our favorite semiconductors, put one on top of the other. And then this is looking at the optical emission spectrum and the structure of one thing going this way, one thing going that way. If you look at the respective emission for this material at the right wavelength, you see plenty of emission here and here. You look the emission for the other material here and here, you're in good shape. But what about this box? The box is where they overlap. You see hardly any emission. This is a log plot of the emission. And you actually see sort of similar features, but very, very strongly suppressed. So that they wouldn't shift a lot is reasonable because the interactions, I mean, I talked about the screening effect, but they're not like dramatic shifts. But why does the signal almost go away? And the answer is that you have a new thing that can be happening, which is that either the electron or the hole in the exciton will hop in the other material, because we understood already that you had the staggered band structure. So then you would separate the electron and hole, they wouldn't be as near each other and they wouldn't emit as well. And this kind of rapid charge separation creates a new state, even in these fairly weakly interacting layers. So this is something that now come to be understood as an interlayer exciton. You have separated electron and hole in the two layers. And I'll just tell you a little bit about some of the, very briefly, some of the experimental techniques we've been using to understand the formation of this and its properties. So in this picture, you expect this to be kind of a prototype of interfacial charge transfer, a very important process in many areas of physics and chemistry. We were asking ourselves, is there a way we can actually see this? So from the suppression of the emission, we infer that charge separation has to be very quick. Otherwise, you would have enough time to emit before the charges separate. But the distance they move isn't very far, obviously. So of course, we see a signature in the suppression of the emission, but is there a way we can look at it directly? And it turns out by using pulsed excitation, so you set this all up at once, you then get a quick current flow. And interestingly enough, you can actually see the radiation from this current flow. So it's like a radio antenna, very, very short. But on the other hand, the acceleration is very high because the charges are moving less than a picosecond. That actually means that you have the very high acceleration and you have emission in the terahertz spectrum. And it turns out if you monitor the electric fields here, near field radiation, there's a quantitative relation between the electric field and the current flow. So we can see that actually the current flow occurs on a time scale of about 100 femtoseconds. And that accounts for this very dramatic suppression in the emission, the optical emission from recombination. And this is just a sort of highlights of some new experimental techniques. The other thing you'll notice is that if this interlayer exciton forms, then the energy of that state is lower than the energy you started. Where did the energy go? Conservation of energy, it should have gone into phonons. And that means in addition to the current flow, you should start the lattice vibrating. And collaborating with a former student, Archana, and team at SLAC, we actually have a very nice way of looking at this thing with electron diffraction. So electron diffraction shows the crystal structure. You get this very pretty thing here after appropriate colorization. But you can actually see the lattice of each of these two layers in the heterostructure, two semiconductor layers, and then you get some spots from these supporting layers here as well. But at SLAC, there's this nice capability of doing electron diffraction with a short pulse. So the result of that is that you actually can trace the amplitude of these spots as a function of time. And when the atoms are excited by phonons, they move, and the Debye-Waller factor reduction comes into play. So that actually gives us a way of looking at the evolution of the vibrations, and we can see where the energy is deposited that accompanies this current flow. Well, I think I will just, if I can figure out how, skip to the, this may be beyond my capabilities. Having so many friendly faces here in the front row, I went a little bit slower. So we'll just skip to the conclusions here. Okay, so just to recapitulate, on the optical side of these 2D materials, hope you'll carry away the idea, because of the reduced dimensionality and mostly because of the very reduced dielectric screening, all the optical excitations are dominated by correlated electron hole pair states, the excitons, and you see the ground state Rydberg states. You see these higher order correlated states like biexcitons, and with the time resolved photoemission, we can also see momentum dark states. The 2D platform is very tunable in ways that often don't apply to bulk materials. I think a particularly distinctive thing is this external dielectric environment, which really doesn't have an analog for thicker materials. It does have a very good analog for molecules, I should say. Local strain was something else I highlighted. And then heterostructures actually support new excited states, and we're coming to learn a lot about them, and also the interesting moiré physics that I didn't really have a chance to talk about. Just like to acknowledge lots of different collaborators. The time-resolved ARPES experiments were done with Keshav Dani's group, theory support, different materials. I should say a lot of the slides I showed date back to my group's work on this at Columbia, which included a really fantastic team of guys who are making my life extremely difficult by doing everything faster and better than we could do. Particularly like to mention that Albert Ragosi here contributed a lot to those early experiments, and thank you very much for your attention.
So I'd like to begin by having Tony ask the online audience for questions. And,
okay, sure. Are there any questions from the online audience? They're either none or they're not connected. Okay, but in either case, I won't have to answer any hard questions.
I'll shift the focus to the people in the room if there are any questions for Tony.
Bill.
So early on at the talk, you told us, well, the spectra of the exciton is not hydrogenic because there's this dielectric screening.
You do this too to have it here.
Right. Okay. So you talked about the spectra not being hydrogenic because of the screening, and then later you showed us this picture about how when you went to higher states, then more of the field that one imagines is between the electron and the hole is outside the dielectric. So what I'm wondering is, if you go to higher and higher states, does it return to being hydrogenic? That is, does it look like a Rydberg spectrum with a big quantum defect, or something else going on?
Great question. Yeah, of course, that picture was sort of the physics behind the non-hydrogenic spectrum, was two sides of the same coin. But yeah, you do already, like the n equals, we could see up to maybe 4 with, at that point, the electron and hole are so far apart that you're mostly controlled by the external dielectric media. And then we would anticipate it looks more like a two-dimensional Coulomb potential. Of course, which is different from it's still the electron and hole are in 2 dimensions,
Yeah.
but there's no modification as a function of distance of the Coulomb potential.
And I was just assuming 2D hydrogen.
Yeah, 2D. Yeah, it'd be a 2D hydrogen. So experimentally, the answer is we don't know, because we don't really see such high states. But it'd definitely be worth an effort. With the improvements in materials, I think that's much more possible now, to look at the higher and higher lying states. And actually, the thing that you didn't see so many of the early wide spectra. Of course, our narrow spectra are extremely wide for guys like you by n orders of magnitude. But for solids, they're narrow. But there's been a lot of improvement just by making the external dielectric environment more homogeneous. So that was actually the major factor that gave rise to line broadening, because if you didn't have, even if the material was perfect, if the external environment was modified, then it would also give you spectral shifts. So it would be very interesting to go back there and try to really extend the Rydberg series and see what we get. It's also quite an interesting regime, because the length scale is going to become much more macroscopic eventually. So thank you for the encouragement. Something we can look at.
So can you say something about the compatibility of the single emitter sources with high collection efficiency?
So the question was the collection efficiency for the single quantum emitters. I don't know that of course they're more or less like radiating isotopically. So it depends what you're trying to do with it. I would think it wouldn't, you wouldn't have a very small collection efficiency to fiber or something like that. There's no intrinsic reason you couldn't incorporate this kind of thing into a waveguide structure also. I mean, one would of course have to think through the logic of the fabrication. We have been looking and thinking a little bit about what happens when you try to strain several layers, and they're actually interesting tribology problems of, do you strain all of them together, or they move with respect to one another? So those would be some of the things one would probably want to work out if you thought of like stacking something that was a waveguide and then applying a localized strain. I think in terms of a quantum emitter platform, there actually are several things people are thinking about. So also, if you produce these interlayer excitons, they have a static dipole moment, and then their energy is very tunable by external fields. So for the intralayer excitons, just in one electric field, don't do that much. But I think that would be another route to do localization, and that probably is pretty easy to incorporate in different kinds of waveguide structures.
Would it be an issue though with spectral wandering?
Yes. The question was, would it be an issue with spectral wandering? Yes. So you maybe need the right balance there.
So,
Yes.
I'm really interested, particularly about biexcitons.
Sure.
So is there any experimental evidence that there is a correlation to the emission of the two parts of the text?
Yeah, so the question was, people really seen like correlated emission of photons from biexcitons. I believe there's one paper, it has not been studied extensively. I mean, you would certainly need to be in a regime where you have high quantum efficiency, otherwise the whole thing will be very painful experimentally. And there's been sort of steady progress, and early on the quantum efficiencies were really not that high, maybe 1% or something. Now there are a lot of reports that's close to 100% if you do the right things. So it would be very interesting to go back to that issue. I should say though, to see those correlations, you'll have to combine the biexciton with localization. So if you have these delocalized excitons, biexcitons, then you're not going to see a very strong effect. So I think you really want to sort of combine some kind of strain localization or something else with biexciton would be, otherwise you can basically get too much of a background from the uncorrelated biexcitons. You look dubious, but maybe we can discuss it.
Yeah, I was thinking maybe instead of coupling directly to that external, one could use an imaging camera or an array of detectors.
Okay.
As opposed to.
Well, it'd be great to discuss this. I think it's very, even though the biexcitons are very clear experimentally, not that much has been done with them actually. When we first looked at this, we created them by having a fairly high density of excitons with the pulse. Turns out in these encapsulated samples where all the features are much easier to see, and mostly where non-radiative rates are lower, you see them very easily with CW excitations. So they're pretty prominent, but people have not really gone the next step. So maybe you have some good ideas.
Any final questions? In that case, let's thank Tony again.